Hello everyone, welcome back to our Grasshopper tutorial. Today we are going to have another lecture for Curve Attractor. Before we start, let's review what we have done last time. First, we generated this grid of hexagonal cells. Then we draw the curve, which is this one. Then we use the distance between each of the hexagonal cell center to the curve as a parameter to set the size and rotation angle for each of the individual cell. And that's it. Today, we want to add more details into this file with the knowledge that we gained from the other lectures, especially from the ones that we talked about the data structure and nested lists. Okay, let's take a look at what we are going to cover today. First, we're going to talk about how to bring another curve like this one into our file. And bringing another curve means that instead of calculating the distance between the center of each cells to one curve, now we are going to calculate the distance between each of the points. For example, this point specifically, we're going to calculate the distance between this point and this curve, and also this point and this curve. And then we're going to use the smaller distance as our parameter to do the calculation. And then we're going to talk about how to add in color and how to add height into the file. So that's it. And let's begin our lecture today. Before we start bringing new components into the file, let's clean up the file real quick. And then let's disable this component to lower the amount of calculations that the computer need to do. Now let's get into the file and think about what we need to do. This is an input for the curves. Right now, you only have one curve, which is this one. And if we select multiple curves and bring two of them into the file, well, it looks like some changes has already been made, but that's definitely not what we want. The reason is here. We're going to bring this panel into the distance. And now what we have 836 locally defined values, and we have 44 groups. Each group have 19 values. This just simply looks too complicated. How about we simplify the data a little bit and make our following conversation a little bit easier? So I'm going to make this into 40 by 20 grid. So now we have 40 lists, and each list have 20 items. Much easier to talk about it. We know that this is not right because now we have 20 times 40 grids, which is 800. We are looking forward to have 1,600 distances in between. Why is that? Because we just talked about our logic. We want to have each point to calculate the distance with both of those curves, and then find the smaller distance for each of those points, and then use that as a parameter. How are we going to do that? Well, it's quite complicated, and in order to explain it better, let's look at some examples here. I generated some examples, and then you can see that on the left, there are a bunch of points, and on the right, there are 2 points. We can use this as an analogy for the points and curves relationship. Although they are points and points, but the relationship or the way of connecting, they are the same. So let's take a look of the data here. First, let's look at the list on the left. We have 3 lists within this big list. Those are list 0, list 1, and list 2, right? Those are the 3 lists I'm talking about. And each list has 5 items: item 0, item 1, item 2, item 3, and item 4. That's pretty clear. And then on the right, we have one list, and this list has 2 items, which are here, right? We just have one list, and this list have 2 items. And then if we make them connect to each other, this is what's going to happen. Well, to make it clear, we can move this point a little bit. You will see that the connecting logic is the following. They will connect the item 0 on the first list on the left to the item 0 on the list on the right. And then the item 0 on the second list on the left to the item 0 on the right. And then same applies to the last one, right? The rest of the items will connect to the second item on the list, which is this point right here. So pretty clear. This is not what we want, right? What we want is that this point will make connections with all the points, and also this point will make connections with all the points. So let's look at another example, which is this one. We have the graphed list structure on the left, and we have the flattened list structure on the right. Again, they only have one list with 2 items, and here they have 15 items within 15 individual lists. And those listing paths are complicated. And let's just ignore it right now. So on the left, we grafted this original data. The original data, we have 3 lists and each list have 5 items. After we grafted it, it becomes much more complicated. Let's look at the path here, which is the index for the lists. We have 3 big lists, and then each of the 3 big lists have 5 sublists. And then each of those 5 sublists have 1 item inside. But long story short, we can just consider this one has 15 sublists, and each sublist has 1 item inside. And on the right, we have 1 list, and this list is flat. It only has 2 items inside. And then they made this kind of connection, right? This is what we want. This 1 list connect with every point, and this 1 list connected with every point. This is what we want. Let's look at another one. We grafted the list structure on the left, and also we grafted the list structure on the right. And let's see what's going to happen. Well, this is what's happening. This point right here is the first item on the right, and it connects with the first item on the left, which is this one. And the second point over here connect with all the left points in the first list. Again, this list here have 15 sublists, and each of the sublists has 1 item. Okay, so the first sublist on the right will connect with the first sublist on the left. And then the second sublist on the right will connect with all the sublists on the left. That's it. So this is not what we want. And let's look at another possibility, which is this one right here. The original list on the left and the grafted list on the right. So this is what's going to happen. To make it easier to see, let's move this first item, and this is what's going on. So they basically connected the first list on the right, which has 1 item, with the first list on the left. So they connect with all the items on the left. And then the second list on the right, which has 1 item, will connect with all the rest of those lists. Again, this is not what we want. So we will clear all the joins and stop this sharing. And then let's look at the last one. The last one, we have flattened list on the left. We have 15 items here. And then we have the grafted list on the right, and 2 sublists within this list on the right. And then this gives what we want as a result. So long story short, let's take a look at what works and what doesn't work. What are working are the second one and the 5th one, which is grafted the list on the left and flatten the list on the right, or flatten the list on the left and graft list on the right. So we can make our conclusion. Flatten one list and graft another one will ensure that all of the items in between will have this sort of connections. And this is actually what we want. But after making that conclusion, let's look at the details of those 2 different examples and see what differences they have in between. This is the second example, and this is the last example. And let's take a look what the final result looks like, or the data structure looks like. The second one, well, we have 15 sublists inside of this list, and each sublist have 2 connections. And on the right, we have 2 sublists, and each of those 2 sublists have 15 items. Well, again, our goal is the following. We are trying to find the distance between this point to this curve, and the distance between this point to this curve, and use a smaller distance as our parameter, right? So it will be easier to put 2 of those distance into 1 list and then find the smaller number. Of course, if we work it on the other way, we have ways to change the data structure from the right to the left. But what if we just get 1 on the left? Just make our life easier, right? But why this kind of differences exist? Why one is 15 lists and each list has 2 items, and the other one is 2 lists and each list has 15 items? Well, let's look at the previous data structure, and it has the answer here. On the left here, we have 15 sublists pre-existed, and then we have 1 list have 2 items, which is 1 flattened list. And when they make connections, this sublist structure will be preserved, right? And then they will make connections with each of the points on the right. So we have 15 sublists to start with. We will have 15 sublists to end with. But for the other example on here, we have 2 sublists on the right and only a flattened list on the left. So this kind of two sublist structure will be preserved. So in the result, we will have two sublists, and each of those sublists have 15 items. I know this sounds very complicated, but it's very important for us to understand how Grasshopper works in terms of this kind of data structure. So this is where we gain the knowledge. So let's make the final conclusion. In order to make this kind of rule applied on our example here, our goal is to graft each of those cells into its individual list, and then we will calculate the distances in between those individual lists and those two curves, right? So we want to graft this one and then flatten this one. But also, as you can see that we have this kind of data structure change here. After grafted, they preserve this kind of data structure that's inherited from the previous time. In order to make our way of thinking easier, we can just flatten everything in the beginning. We just flatten this data structure. So we get rid of this 3 sublists, and each sublist has 5 sub-sublists thing, right? We just make our life easier by doing so. We just flatten everything in the beginning. The final result will be kept, and then the final lists will be easier to read. Okay, so let's apply this kind of knowledge we have learned here to our original file. Again, let's lock everything, because if we make a mistake during the connection, it will become a nightmare. So let's first flatten everything, see if it works. Let's flatten those cells, and let's flatten these points and turn it on again. Well, okay, so this kind of result still being preserved. And then let's start to graft things. Again, remember, we want to graft all those points, and we want to keep the curves flattened, okay? So what we need to do is we will type in a thing called graft. We flatten things here, just simply toss all the listed structure from the previous time, right? So make our life easier, as I mentioned. And then we will graft those lists by using graft. And then we will replace everything we have here with those grafted data structure. So again, I'm going to lock it. And let's take a look. Well, this looks completely chaotic. Why is that? Again, let's take a look of the data structure. Because for the geometry, we have 800 geometries. For the center of scaling, we have 800 values, but each value has its own individual list, right? And then for the scaling factor, we have 800 lists, and each list have 2 items. So this kind of mismatch will make 800 times 800 kind of connections, which is not what we want. So we need to graft this one first. And then this is what it looks like. But again, this scaling factor is completely wrong, because we want to have 800 values here, 800 values here, and 800 values here. But now they have 1600 values. What we need to do is we need to find the smaller values in each of those lists. So let's take a look. See, we have 800 lists within this list, and we want to find the smaller number on each of those sublists. In order to do so, we need some other components. First, we need this thing called sort list. Okay, it's right here called sort list. Let's plug it in, and let's take a look what this is going to do, right? Sort list, and let's pull it to the end. So on the left, we have 41.6 and then 41.1, which is the last sublist in the original list. But after we use sort list, it's 41.1 and 41.6. This one, 39.7, 37.6. On the right, it's 37.6, 39.7. See, they are trying to put the smaller number on the top, put the bigger number on the bottom. So what this component is doing is that it sorts a list of numeric keys. Basically, it means that it will put the smaller number on the top of the list and put the bigger number on the bottom, which is exactly what we want. We want to find the smaller number. So we can use another thing, which is our old friend called list item. By default, it will choose all the index 0 item in each of the list. And then in this case, they are all the smaller numbers on the left. So that's what we want. And then we need to replace these distances with the new data we just generated. We will plug this one in, plug this one in, and plug this one in. Okay, so this is the final result. Let's hide everything else and take a look of what's going on. So now we can see that the result of those scaling and rotating is not just affecting by one curve, but rather two. If we move this curve, it will also affect the final result. And if we make it approach it again, and if we take this curve away by moving it so far, at this situation, only the distance between those points to this curve count. So it looks like this curve doesn't even exist. But once we bring it in, and then it get back to the calculations again. So that's the thing we want to learn here in terms of how to bring another curve. Again, bringing another curve is not the point. The point is to learn how to use those rules of connections to make things as what we want. So the next thing I want to share with you is how to add colors into this kind of system. The easiest way of adding color is just use custom preview and then bring the items you want to add the color in. By default, they have this little purplish color, and I don't want that. So I can just use color picker and change the saturation, change the hues, plug a color in. I can change the display mode, and I can hide all the grid. Come over here and hide everything. Okay, well, I still don't like this uniform color. So is there any way to keep those gradients into the color change? Well, there is a thing called gradient. Let's take a look of what this is doing. It's called represents a multiple color gradient. So we have the lowest limit of the gradient range, upper limit of the gradient range, and the parameters. Well, that's exactly what we did here for the factor, right? We have lower limit, we have higher limit, and we have the values. So I will just plug those remapped thing into the system, and then I'll plug those final result into our color. And then this is what's going on. Well, this one doesn't look that obvious. We can change it. For example, this one, right? And then if we call back our curves, we can change the color by moving the curves around. Or we can change the color gradients by changing those data points. So what this thing is doing is that it finds the lower limit and the higher limit of this domain. And then, for example, the lower end here is 0.2. Higher end here is 0.938, right? Which are those two. And then those are remapped data. For example, if the remapped data is 0.4, it's somewhere here. And then for this specific location, they will pick up a color here, which is this yellowish color, and then bring the color into our custom preview and then show this color to the specific item. For example, here, that's how this gradients is working. Okay, so some very handy tool that you can use it in the future. And then we can use the same logic to change the height of each of those cells. Well, how are we going to do that? We can simply use the thing called move. There are two inputs. One is the base geometry, the geometry you want to move, and also is a vector. And then we can find a component called unit z. It's basically a unit vector paralleled to the world z axis. We go to the front view. It's just a unit vector point to the z direction. All right, this is basically what this is. It's a default z direction vector. And then we can change the values of these vectors. And then we can use those values to generate a bunch of z direction vectors and then plug it in. So here are the geometries we want to move. By default, it will move to 0, 0, 10, which is 10 units along the z direction. But now we don't want to move it 10 units, but rather we want to use those remapping numbers as our input. And now I will just copy a bunch of them and come over here and bring this remapped number into the z units. And then plug it in. Okay, so now because our limits are very low, we can make it much higher by change it to, let's say, 100. We can change the display to ghosted, and then we can change it to 100. And then we can also apply this kind of color gradients to the lifted items. Let's hide this. Let's bring back to the display mode and hide everything else. Okay, so this is what we're going to get at the end, right? And let's unhide the curves we can change the base geometry, which are the curves, and change the final result based on that. Isn't that so cool? Yeah, that's it. That's what we're going to talk today, which we talked about how to add another curve. And during that process, we talked about different mapping rules between grafted and flattened data tree. And also we talked about adding color, and also we talked about adding height into the system. One thing I want to recite with you is that the reason we flatten everything here, the reason is here. For example, this one, it has an original 3 lists, and each list have 5 items data structure here. And if we don't flat it and simply graft it, we will have a very complicated list path, which is 0, 0, 1, 0, right? Which means there are 3 lists, and each lists have 5 sublists, right? So there are list within the list, within the list, within the list, this kind of data structure, which is not what we want. We want to make our explanation clear in order to bypass this kind of list within the list, within the list, within the list chaos. I just simply flatten the original data. We throw out all the original list index and then graft the end, which is this one. We basically get rid of all the 3 lists, and each list have 5 items, this kind of data structure. So same here. If we don't flatten everything in the beginning, we have to be a little bit more careful once we are changing with the data. So for example, if we don't flatten them in the beginning, nothing will change really. But the data structure that we are talking about here will be more complicated. You can see that there are 0, 0, 39, 19, this kind of data structure, and I don't really want to read about it. So that's what you need to know. Again, a lot of details are very, very hard to be explained very well. I'm trying my best to make it as clear as possible. But if you find something that you don't really understand very well, don't be worried. And you can always come back to me and we can talk about it more. Thank you so much.